Okay, you're good to go.
Yeah, good. So, this is a tutorial which the title is a little bit of a misnomer because when I started preparing it based on feedback from people I talked to, actually this is more like about internals of blockchain. And of course, we will look in more detail at permission blockchains. And the reason why permissioned ones are more relevant for databases, you will find out during the tutorial. And then the second part of how to build applications with Hyperledger Fabric. This is something because of the time I decided I will give you an overview of some exercises, but then you will be able to download the virtual machine and some exercises, basically some GitHub repositories that have small applications in them with some exercises, so you can take your time at home and try it out. Or alternatively, if you have ideas of projects that build on this, you can take these applications and extend them. So just to give you an introduction of myself, I'm an associate professor at the ITU University in Copenhagen. I'm part of the Data Intensive Systems Lab. And my, let's say, relationship with blockchain comes from a postdoc I did at IBM a while ago, and then some projects that were going on understanding how hardware acceleration could be applied to permission blockchain. So I worked with FPGAs and things like distributed, like a consensus or networking acceleration, and as an emerging application, which of course is by its nature very much distributed, I was interested in understanding how things can fit in with permission blockchains. I will not actually talk about this, or I have not prepared slides, but if you're interested, we can also, I can give you a 5-minute overview of what the lessons learned were there. And then just to give you again the context of how I'm looking at this, I will not sell you cryptocurrency. I will not convince you to give me money for my initial coin offering. I'm really looking at blockchain as a curious database researcher. I'm not a big fan of like religious arguments or this kind of things that come about in blockchains. I'm really looking at it as a database researcher, trying to understand how the technologies that we so dearly like and understand, and perhaps even developed ourselves right in the database community, can apply to blockchain, or the other way around, how some of the ideas from blockchain can be used to make our systems more resilient to faults or more trustworthy. So here, I mean, I prepared like an online poll, but given that we have only a few people in the, actually let's do this because maybe people don't want to unmute themselves. So I have just prepared this poll. You can go to menti.com and use this code here. It's you don't need to log in or anything. This is you don't need a user, just enter it in the browser and answer these 4 questions for me, please. So this is just to get a feeling for where you are with blockchain. Okay, so let's see, the votes are coming in. So it looks like it looks like most of the people have some idea of blockchains, but the the internals that we'll talk about that hopefully will be useful. And then yeah, I'm happy to see that that there's little experience with Fabric, because I think with if you wish to improve that, then with the virtual machine image and the exercises, you will be able to do so. So let me see, is anybody still voting? Probably not. Okay, so I think this is perfect. You're in good hands. So let's go on. Okay, so the first thing which I want to highlight is that when we talk about blockchain, we often think about Bitcoin, and it's I think it's super important to stress that that Bitcoin is not equal to blockchain. So if we want to give a definition, basically a blockchain would be a data structure, so distributed ledger combined with a consensus algorithm. And depending on how we choose or what flavor of these parts we choose, we can get different blockchains. Bitcoin is one specific, let's say, instantiation of a blockchain, but there is many other types, and this is what the tutorial will cover. So if we talk about the distributed ledger, perhaps this is something that some of you are already very familiar with, but just bear with me so that we go through the basics. You can think of this as an append-only log. So from databases, clearly we know this data structure, but you can think of it in like banks for money transfers, right? You can also think of it as a medical history, where basically we are appending in order to a sequence of data entries. And the distributed aspect, so the ledger is basically the append-only log, and then the distributed aspect comes from the fact that it's designed from the get-go to be residing on several distributed nodes, which provide durability, high availability, and of course, the main use case for blockchains is to share data across organizations or across entities. We will see more detail on this later. So this is really, if we just look at the data structure at the core of any blockchain, it will be a distributed ledger. And the way, with the naming where the blocks come from is really rooted in how internally this ledger is structured, so that it can provide some kind of verification for data correctness, so that the data has not been corrupted. And here, if you see in this example, what we have is typically data blocks which are linked together through fingerprints. So each block will have a fingerprint, and then the next block will reference this inside. So this way, if I have this chain of blocks starting from the end, I can basically verify. Starting from the other end, I can verify that this chain is correct all the way. Right. So the point here would be that that this data structure doesn't allow modifications of previous blocks, because if I would change the data here, the cryptographic fingerprint of this block would also change, and then the next block would not. This linkage will break. So here again, I don't really know the exact background of people, so just to give like a cryptographic refresher. So the way these hashes are computed is basically through hash functions that the main property here is that once I hash a block or some piece of data, this is not reversible. So knowing just the hash value, of course, I cannot guess the data block itself, and it's collision resistant, which means that it's extremely difficult, so basically impossible to create a block which will have the same hash as an existing block. So this means that it's very hard, again, practically impossible to tamper with this data structure. The other very important part in any blockchain system, regardless whether it's a cryptocurrency or it looks more like a data management problem, is the use of public key cryptography operations. And again, this is just a refresher to make sure we're all on the same, we are on the same vocabulary. So what we can assume is that in all blockchains, every actor, every piece in the system has a public and a private key, perhaps several, and this is not to be confused with identity. So this basically, this just means that I have some key pairs that actors use. And then in some kind of blockchains, you also rely on a key authentication authority, which can match a key or a series of keys to an identity. But what this public key cryptography allows us to do, on the one hand, is to encrypt data, right? And this is done by taking a plain text message and then using. So if Bob wants to send Alice an encrypted message that only Alice can read, then Bob can use Alice's public key to encrypt it, and Alice can decrypt it with its private key. So this is, of course, something that perhaps you all have seen. But then you can also use public key cryptography to sign messages. This means that Alice can prove to to Bob or to anyone else that they have actually, this message, hello Bob, was sent by them. And how this is done is by taking, for instance, the hash of this message and encrypting it, so to say, with Alice's private key. Then anybody else can decrypt this message with Alice's public key, which is public knowledge, right? And can verify that the message indeed came from Alice. So this is something that, regardless of the type of the blockchain, signing and verifying is a very fundamental operation that nodes will do. Again, just to reiterate, the presence of private and public keys doesn't mean that nodes have identities. It just means that we know that that person who signed this message was had this private key in their disposal. We don't know, we don't necessarily know who this person is. We just know they own this private key. So this is something that we can talk about maybe at the end, about wallets and how, for instance, Bitcoin transfers are made. It is very intimately intertwined with this private and public key setup. Okay, so we see now that we can basically we can have a data structure that that forbids modifications and deletions, right? So we cannot really tamper with it. We can verify it very, let's say, in a simple manner by reading the blocks and then computing some hash and checking that things match up. Now the question is, how do we actually add to this data structure? So of course, if we think of if we take a step back and we don't think about databases anymore, but we think of a system where anybody and everybody can speak up, you could have nodes you could have actors in the system who would like to introduce garbage information into this ledger, right? So maybe it is in your interest to put some kind of logically wrong information into ledger. So writing to this data structure in an unchecked way so that anybody can just add to it is not realistic. So that's why every blockchain will use some form of consensus so to say, and I'm a little bit, I'm oversimplifying things, but so to say, to decide whose turn it is to add to the ledger. And all blockchains will come up with some consensus mechanism that aims to give equal chance for actors or nodes in the system to propose rights into the chain, and most of them will strive for a form of majority rule. So basically, for some mechanisms or checks that are in place, that the majority of the nodes has to agree that what we're recording into the ledger is actually correct by some definition of correct. So not only that the hash is checked out, but the information that you're recording into a ledger is not garbage. So also, if you have any questions, feel free to raise your hand or write in the chat or just stop me. Okay, so now we come to a little bit the taxonomy of blockchain. So depending on how we give access to this data structure and the consensus, we can have different types of blockchains. So depending on the access to the network, so overall, whether you can access if you can be part of a blockchain, we differentiate between public and private systems. So you can think of a public system where basically anybody has read access to the blockchain network. So apologies here, I use network maybe in it's an overloaded term. So I refer to the to the distributed ledger and basically the interfaces that are around it. So yeah, a public system is where, as I said, anybody by knowing where the ledger is, I can go and read the data. And the private system would be where a consortium or a third party will basically give access on a node per node basis or person per person basis to this data structure. And then depending on how the nodes participate in rights or participate in consensus, we can have permissionless systems. So this means that any participant can initiate a write to the ledger, right? This doesn't mean that this will necessarily go through and be recorded, but at least any participant could initiate a write. And then we have so-called permissioned systems, where only nodes who have been authenticated, given the right to write to the blockchain can do so. So if you look at the use cases, and of course this is in no way exhaustive, but I just want to give you some feeling, right, of the different combinations of this access rights. So in the permissionless public space, we have things like cryptocurrencies and censor-free publication, or putting art on the blockchain and then bidding for it, and putting your name tag next to it. So the point here is that by design, the systems want to allow anybody to access the system, and anybody should be able to propose transactions or propose rights to the ledger, whatever that means, whether that's a money transfer or whether that's a recording, that I bought an artwork from someone else. Now, if you look at the public permission space, these are systems like, you could have payment systems like Facebook's Libra, or you could even imagine Visa as something where we basically want to allow, to some extent, the general public to access this system. We don't want to put very strong checks on who can access the system, but in terms of making rights, we are more selective. So maybe perhaps notarization is the best example. Like within the European Union, there's works in trying to put, for instance, university degrees or on the blockchain, or the vaccine passports. I think that's another example of a public permissioned blockchain, where you can imagine that this is a publicly accessible system, and for instance, the cryptographic hash of the vaccination passports are uploaded by selected entities. So this would be governments or medical institutions. So that's the permission space. Of course, this doesn't mean that you're storing all the information on plain text in the blockchain, but perhaps you store enough information in the blockchain that anybody can verify whether a piece of degree, certificate is valid or not. Then we have private permissioned blockchains, which you can think of as examples are supply chain management or shared databases across companies. So here, the information is not really targeted at the general public, right? Here we can be very selective of who actually has access to the blockchain, and then we are also very selective about who can modify data in the blockchain. And then the private permissionless space, that's something that I couldn't really come up with any use case where you are, yeah. So this is something which I think it's it's a gray box here, because it just doesn't necessarily make sense. From a database perspective, I think most of our use cases where we think of databases, we're in the private permission space. However, there is one fundamental difference between blockchains and databases, is that typically in databases, we assume that all nodes of a distributed system, of a distributed database, belong to the same organization or are under the same governance. Whereas with blockchains, there's a decentralization of trust. So basically, all nodes in the system might belong to a different company, different governance, managed by a different entity. Okay, any questions so far? Anything which, if not, then let's look a little bit at permissionless blockchains. So these are, Bitcoin is one example. These systems are geo-distributed by design. So the idea, as you remember, permissionless public blockchains are designed to be accessible by anyone and everyone. So this means that nodes will be all over the planet. And also the ecosystem, what I call here, is rich by design. So you would want, for instance, multiple clients to exist, right? You want your mobile phone or your laptop or server to be able to connect to this network if you wish so. So if you look at, for instance, Ethereum's distribution of clients, so the Ethereum ecosystem where nodes are running, you can see that there's one, let's say, dominant implementation, but there's many other types of implementations that talk across each other and keep the blockchain going. So with permissionless blockchains, the problem is that we have a little bit of a trouble with consensus, because the way we think about it traditionally doesn't necessarily hold. So imagine if we say that we need to reach 51% majority decisions on what to add to the blockchain, but it's not entirely clear, first of all, who are participants, right? So if you think of churn, it's extremely high. We can have, depending on when people have their smartphones turned on, or their laptops or workstations turned on, we can have more or less active participants, and there's no really way of knowing who are these. And then it's also unclear how you can actually differentiate between the participants. So is IP address a reasonable way of doing so? Probably not. As you probably have heard, this notion of a Sibil attack is basically the danger that you have a malicious actor who creates a large number of fake identities, of fake participants in the network, and by simply flooding, getting up, for instance, a very large number of IP addresses for nodes, can gain an advantage, basically having more than the half of the active nodes voting. So this can mean that if I just would go with majority in such a public permissionless blockchain, it would be very easy to subvert. So as a solution, different types of ideas come up, and I think proof of work is one that perhaps was one of the first practical solutions. Well, one of the first solutions that works, and it was proposed in the seminal Nakamoto paper. So if we want to look at proof of work as a very high level explanation of what this does or how this consensus works, basically it goes in 4 steps. So first, anybody who wants to add some information, some transactions to the blockchain will set out to solve a cryptographic puzzle. The first one who solves this puzzle, so of course the puzzle looks a little bit different for everyone, right? So depending on what you want to add to the blockchain, your puzzle will be yours. And whenever somebody finds a solution to their puzzle, they send this out to all participants. Participants can verify very cheaply whether the puzzle is correctly solved. And if it is, then they will add this block. They will add this information to the blockchain and restart at step 1. So this is, in a very simplified way, this is how proof of work works. What the proof refers to is that you prove to the others that you have performed the work of solving the cryptographic puzzle, and this allows you, or this makes it possible for you to add your proposed transactions to the blockchain. So if you look a little bit at in more technical details, what we call the nodes working on these cryptographic puzzles are the miners. This is in the Bitcoin terminology, and what miners do is they in every iteration they form a block, which is based on, as you recall, some metadata which is like referring to the previous block in the blockchain. So this basically defines where this block would be positioned in the chain. It will have transactions proposed through the miner. So you can imagine that if I want to make a transfer, I can ask a miner to put my transaction in their block, and then they will have a randomness there that this will actually be used for the puzzle. So the puzzle itself is finding a random number for this block, of like a random like a random salt that leads to a hash of the block that has some property. And the property here for Bitcoin is that it has some number of leading zeros. So you can imagine that the miner, what it will do, it will hash the block, right, with the different information in it. And it can change this randomness here at the bottom. And as it changes the randomness, it will have different hashes coming out for this block. And it will have to repeat this until it finds, for instance, 4 leading zeros in the hash value. So this is by, if you look at the probability, if you require, for instance, 1 leading 0 bit, then you will have to do on average 2 tries, right, to get one. And as you increase the difficulty, as you increase this n, you will have to repeat this hashing more and more times. Now you can see here that the verification of a block is actually, the cost is linear in the size of the block. And if the system has a constant size blocks, then basically this becomes a constant cost operation. You can just take a block, compute its hash, and if the if you get this number of zeros, then it has been verified, and you can treat it as correct. The way this works is that the miner, of course, will include some information here in the metadata, which, for instance, will claim, like if this is Bitcoin, each block will have some inherent value in it, and in the metadata, the miner will claim this value, right? So the way this works is that you prepare all this information and then start hashing with random numbers here until you find a good hash. You send it out to the others, they verify it, and then you all know that this block is correct. Now, the problem with proof of work is that it's actually, as you can imagine, it does some extra work, right? It does this repeated hashing. So to take a small, just a small break, I want to ask you again to vote on a question. So if you go to Menti, which I'm just curious to see, what's your feeling for how much more expensive is a Bitcoin transaction when you compare it with a Visa or a MasterCard transaction. So let me actually just hide the results while people are voting. So I'm really just interested in the order of magnitude. So just, I'm curious what what people's feelings are.
So is this organized as a poll?
Yeah, sorry. So for the ones who joined a little bit later, so if you go to this menti.com website,
so
you
it's
just
through the Zoom link. Okay,
yeah.
great.
I can. Yeah, it's there's no user. You don't need to create a user or anything. It's just a web interface.
So one quick question: how can the nodes agree on the n leading zeros? Because I think n can change over time, right?
Right. So that's something that there's different ways. So for instance, in Bitcoin, the system is designed like the core of Bitcoin defines how n is chosen. So basically, it will try to find basically detects if this cryptographic puzzle becomes too easy to solve. So for instance, a transaction is proposed too often, then it will increase the difficulty. And once it is, the average time to add to the blockchain reduces, then it will reduce the difficulty.
So each node may come up with like a different value of n's, right, in a round.
So again, this is something that perhaps we can come back to later, but you can imagine this as being baked into the protocol itself, like it's
just to make this a little bit, because I think it's a little bit ambiguous, because expensive, you have to define expensive in terms of IO, right? Not in terms of money, because when it works out.
So you will see, I show you the number in a second. So expensive here is, I mean it as in basically joules. I mean it as in financial cost on humanity for running this, right? I mean it as power that you pay for. So I see people are going on 1,000 times more expensive. So this number, it appeared a few months ago. So this is from Statista, and it shows that if you do the number crunching, in terms of energy consumption, one Bitcoin transaction is 500,000 times more expensive than one Visa transaction. So this comparison here, one Bitcoin transaction takes around 741 kilowatt hours, whereas 100,000 Visa transactions take 5 times less. So there's a 500,000 multiplier in between. So to put this in perspective, if you pay for your pizza with Bitcoin, the cost of this Bitcoin that you paid for the pizza is around, I think it was the last number I saw, like $1,000. So this is the true cost on humanity for running Bitcoin. Again, I'm not, this is not about me convincing you whether we should be doing this or not. I'm just highlighting that the proof of work is a very costly mechanism. As you can imagine, if we look at it, and costly not in IO or anything else, it's costly because we're repeating computation, right? We're running CPUs continuously computing these puzzles, and the problem is that we are all miners basically compete for the next block, right? So it's not that you can do work in advance or that you can do sharding, so to say, but you really need to you can only work on the next block. You cannot work on 3 blocks down the line because you don't know what the others in between are. So if we look at some other number for the
cost of Bitcoin transactions is linear, in the sense if you had 10 Bitcoin transactions, it will be 10 times the cost. You are not having any cost sharing.
So that yes and no. So basically, because you are working in blocks, you have some batching. So there's some, like up to some point, the cost of 1 transaction or 10 transactions is the same because you're paying for the block. But since in Bitcoin, for instance, the size of the block is fixed. Again, it comes from the system. It's somehow baked into the system. There's not much you can do, right? So maybe the $500,000 number, you could like massage it down to 100,000 times less, or you could go to 1 million, depending on how you define, the assumptions. But what I really want to highlight is that because of this proof of work does repeated computation that most of the time is basically worthless, it is extremely power hungry.
Okay.
Dimitris, you had a question?
Zsolt? Just one comment. So this is also proportional to the size of the proof of work. Obviously, relates also to the size of the blockchain. Bitcoin is relatively, let's say, smaller blockchain than what these blockchains can become in the future, right? If you have a 100,000 node blockchain, it will be much more. The power will grow even more.
Right.
But
so
my comment earlier in respect to the question was that when you say transaction, somebody can also think about the banking transaction, because these bitcoins and the pseudo currencies, they basically claim that the banking transaction, not the database transaction, is different, right? It's cheaper to do it with Bitcoin payments rather than.
Yeah. So this is something where, of course, this comparison is with credit card. So this is Visa. So this is not banking transaction.
Yes. So
because Visa takes some of the overhead. You're right. But I think, again, if you think of it fundamentally, and this is maybe, we shouldn't get sidetracked too much on Bitcoin here, but fundamentally speaking, the argument cannot hold, because you're, as you said, if you have more nodes in the network, your power consumption goes up linearly with the number of nodes, right? If everybody is mining. So there's no way in which this can be more efficient than running, a regular consensus across a handful of banking servers.
Just one thing to comment about is, in the real world, the proof of work is carried out by humans, right? And here in this blockchains, the proof of work is carried out by the system in a very inefficient way, as you say, because there's a lot of repetition.
Yeah.
Also in the real world, there is inefficiency. Like the humans might also be inefficient in the way they clear a transaction in a banking institution, let's say. So, but just to generalize this and have a better picture of.
So I think so that is true, but I think what we're we shouldn't be comparing Bitcoin to banking transactions, because if you recall the taxonomy from the beginning, banking doesn't sit in the same box in terms of, so banking would be still a permissioned system by definition. Like you can banking is a system where you can have some identities, and you should have some identities, and that's what makes the problem fundamentally different. I'll get to there in a second. So if you bear with me, when we get to permission blockchains, I think that is a better comparison. So Bitcoin, I don't see it as a real currency. I think Bitcoin, and this is now we're really going on the side of the discussion. Bitcoin is basically some kind of speculative tool. It's not, this is not, if you look at payment, in many ways, it doesn't fulfill the goals that were set out. But let's, let's focus on the technicalities now, and then maybe we can have a discussion at the end. So if you look at proof of work, one other problem, which from I'm not saying this is fundamentally bad or good. I'm just saying for a database person, what makes proof of work problematic is that there's no transaction finality. So what the blockchain does, it will always take the longest branch. So you can imagine that because to add the block, I need to reference the previous one, right? I could have two blocks which reference the previous one, and this could, I can verify the blockchain either going to here or either going like this. This is both of them are valid. So what happens is in most systems, by virtue of let's say tuning the system, people have agreed, or the system agrees, that it takes the longest branch as the true, as the true fork. The others are considered as basically dead lines, and they are not, the real state is in the longest branch. Now the problem is that you can never reach transaction finality as a database person would think of it. So it is only probabilistic, because at any point you could have this, you could discover that there's another branch which is longer than the you are on. So this sounds like a conspiracy theory, but imagine if somebody forked the Bitcoin blockchain 2 years ago and has been secretly building an alternative reality, and at some point we release that it has a fork which is 5 blocks longer than the current one. This will result in everybody having to throw away all the 2 years worth of transactions they had on the blockchain and switching over to this new reality. This is a fundamental property. If you go, this is a probabilistic data structure in that sense that you cannot have true transaction finality. And then, of course, there's the economic problem, which on paper, blockchain looks good because it allows people to freely. Permissionless blockchains with proof of work look like a method to allow people, for instance, to circumvent censorship and be able to put anything on the blockchain. However, in reality, mining has become such a business and so expensive that the people who transactions proposed by users are at the mercy of the miners. So if a miner doesn't want to accept your transaction and not include it in the block, your transaction might never make it into a blockchain. Of course, the reasoning is that there's an economic incentive to miners to do so, but that is tricky, right? So there is also assumptions like mounting a 51% attack is very expensive, so it will never happen. Miners will not collude, so on and so forth. If you look at the reality of, for instance, Bitcoin, most of the mining power is in 4 to 5 pools. So pools are basically groups of people who work together, basically parallelize this puzzle solving so that they can be the first to solve the puzzle. If one of the miners finds gets the reward, they share it with the others in the pool. And now, if you look at this graph, the problem is that the top 4 miners might be in the same country and might be under the same jurisdiction of a government. Now, if this is a government which is, for instance, not very nice with its people and might impose, let's say, things forcefully, you could imagine that this supposedly public system, which gives everybody an equal chance, actually can censor transactions. So again, I might sound like I'm talking against Bitcoin. I'm really not trying to make a statement here on that. I'm just showing you that this is all, all these arguments are more in economics and game theory than about technical challenges. Okay, so just before we go for the break, another way of doing consensus in the public permissionless space is by embracing the fact that this is an economic problem, or game theory problem, and switching over from proof of work to proof of stake. So proof of stake, the idea is that those players in a blockchain in the system who own a large amount of the cryptocurrency or assets in the blockchain will want this system to be stable and well functioning. So basically, the nodes in the proof of stake system will propose and validate blocks. Proposal is similar to mining. Of course, there's no cryptographic puzzle to solve. So this is more like I just bring a block and I say, okay, let's put this on the blockchain. And you collect fees from everybody who wants to put a transaction inside your block. And then validation is really what makes the blocks, let's say, trusted or accepted on the blockchain, where people who have put up their money, so to say, to stake, right? They will validate the blocks. And once a threshold count of validations has been reached on the block, we consider it trusted or correct. So in some systems, this could be 100 or 200 nodes that people use for validation. The staking notion is that if you are caught validating a malicious block, you will use your stake that you put up. So you will basically be punished for doing funny business. Now, here there's different, like again in proof of stake, there's many different alternatives of how to actually choose who can propose. So some systems in the earlier iterations of proof of stake or early ideas had a setup where you could basically, anybody who staked could propose things to be added to the blockchain. Nowadays, probably the more acceptable form is delegated proof of stake, where basically you have where nodes delegate their trust, delegate their stake to some larger, let's say, larger players, and then these run the consensus. As you can see, this is much more efficient than proof of work because there's no repeated cryptographic puzzles to be solved. But it also is a very different operational model. It is all based on economic incentives. Even so, proof of stake will not give you finality either. You can at any point discover that a block that has been endorsed was actually endorsed, or verified was verified in a malicious way, and we have to remove it from the system. Okay, so to wrap this up, before we go into the permission space, permissionless blockchains typically are used, or are only used in the public domain, where you have almost no onboarding process. They provide pseudonymity, but not privacy. So if you think again of Bitcoins, I said you have you don't have identities, so you don't know who key pairs belong to, but the data itself is public. So if I can somehow correlate transactions across each other and trace them back to some information that it ties them to an individual, I can actually de-anonymize these operations. From a database researcher perspective, I think what happens is the way we think about latency. So again, this is now very much geared as a a systems person or a database person thinking about these things. Because there's no transaction finality, latency is a different discussion. So suddenly perhaps the latency of a single operation or single transaction added to the block or whatever that is less relevant than the mechanisms we use to decide what we consider first as the longest chain. Also, because the systems are by design, are designed or run and operated in widely geo-distributed settings and across a wide range of devices with different software running on them, often the throughput of these things will be limited by the bandwidth available across the nodes. And then in some systems, like in proof of work, the throughput itself will be limited by the parameters we choose, for instance, for the proof of work difficulty or other factors. So these are, again, you can think of it as built-in rate limiting for one reason or the other that these systems have. So the biggest use case is things like cryptocurrencies or fully virtual assets with examples of Bitcoin, Ethereum, or Tezos. Okay, so with this, I think we're just at the Q&A part. So maybe we can take now some minutes for some questions, and then in the second part of the tutorial, we'll look at the permission blockchains, which are more, I would say, more familiar to the database people and actually have more ideas which permeate between the two. Okay, but with this, let me stop talking and let you ask questions if there's any.
Zsolt, this is Bernard. I do have a question. Can you hear me?
Yes, please go ahead.
Thank you for the nice overview. The technical question is, what is the rate of block building currently for permissionless blockchain? And I came a few minutes late. What will be shown in the rest of your tutorial?
Yeah. So
Yeah,
so,
go ahead.
So the rate of the block building, of course, depends on the, as I said, depends on the specific system and the parameters. But you can think of, this is in seconds, if not minutes. So as I said, for various reasons, either that the system has to do a lot of, let's say, repetitive work to get these blocks built, or there's a economic or game theory reasoning that actually allowing these blocks to be added too quick will not be beneficial for safety of the network, or because in proof of stake you need, let's say, 100 something validations to accumulate before you can treat the block as being added. You can see that here the rate at which you add to the system it will be in large multiples of the actual cost of producing this block, right? So you will have the actual rate of adding to the system will be decoupled from the like underlying cost of producing a block. It's in, as I said, seconds, if not minutes. In terms of structure of the tutorial, what we will do in the second part, so we covered public permissionless blockchains. In the second part, we'll look at permissioned blockchains. So these are the ones where nodes have identities and they behave much more like databases. We'll look at a little bit of how smart contracts work, just a very quick overview, and then how internally one of these permission blockchains actually looks like. So how Hyperledger Fabric executes transactions, how it is organized, so that to give you a more palpable feeling for how these systems actually resemble a lot databases. And then, because unfortunately this is only 2 hours, I would just give you pointers and a very quick overview of some take-home exercises. I've prepared a virtual machine with Fabric installed and with some toy applications already built for you that you can take and do some exercises on. So that would be the second part.
Thank you.
I have some very basic questions.
Yeah.
Do the blocks for a particular application somehow have a fixed schema and size, or is the size varying, and can the schema vary?
So this is, again, I would say this is more convention than anything else. So the blocks themselves, depending on the type of blockchain, can have a very strict schema. Like in Bitcoin, basically every transaction inside the block will be a UTXO, so an unspent transaction output transaction, which has a very specific format, and they will be like that. You could also design a blockchain where you have arbitrary blob information in the transactions, right? So there's no fundamental thing stopping you from doing one or the other. Typically, it will be more on the well-defined schema format. Again, not for technical reasons necessarily, but for convention. Size is something that in the permissionless space is a delicate. There's a delicate balance, because you need to do so. The way these systems disseminate the blocks is through gossip. So there's no central. As you see in the system, like a blockchain doesn't actually have, there's no centralized point. So in order as a node to, for instance, get the blocks, you will have to somehow find other nodes which are, let's say, advertising themselves, right? And then pull the blocks from them. So there's gossip, like peer-to-peer transactions here, peer-to-peer operations. And for this reason, the blocks tend to be larger, so that you have less metadata, you have less housekeeping when you're doing this gossip, right? It's easier to deal with 4 megabyte pieces of information than with the 2 kilobyte piece of information in an internet setting. So in the permissionless space, blocks are typically large. Also, if you think of proof of work, you have to. It's an expensive operation, the cryptography puzzle, and you want to amortize the cost as much as possible. So you want to have larger blocks so that you can stuff more things in, right? And because the hashing itself is not the hashing which gets much more expensive if the block is a bit larger. It's a linear cost. The problem is you have to repeat it many times, right?
So does a block contain a single transaction or a set of transactions?
It contains a set of transactions. again, by convention, in the permission space, and we can talk about this if you want. Actually, there's a fundamental question whether there's a value in batching more transactions in a block or not. So we have done work, for instance, where we propose that applying the well understood streaming processing notions from databases and data systems, you could actually replace the blocks with transactions being chained together directly. So you can operate on a transaction per transaction basis in a permissioned system that you will see in the second part of the tutorial. If you make in the permission system, basically if you make the computation, or like you calculate the cost of doing these operations, it will not be very different whether you do it on a transaction per transaction basis or you batch several transactions together and then you get them through like this. So you can think of this in database terms as batching. So, you will amortize some cost by putting more in a batch, but in some sense, there is no fundamental thing stopping you from going to a batch size of 1.
Is there any kind of indexing on the set of blocks?
Yes, you will see. So this is, again, you're asking all the right questions. So in the permissioned blockchain, of course, because you are looking at this more as a data management problem, there will be basically like a materialized view of the state in the blockchain. In things like Bitcoin, the transactions themselves might be there's a different representation. So it might be a history of transactions. So you can build an index, but the system itself, let's say, is not directly supporting this, right? So you could have clients which then take the data out and build an index and do something with it, but the system itself doesn't require an index for its operation.
Is there any other question? Yeah.
I wanted to suggest that we take the 10-minute break for coffee and whatnot, or is it 15?
Yeah, it's a 15-minute break. So thank you very much for the presentation. We have a 15 minutes break before we come back to part B of the tutorial.
Okay, so see you in a bit.
Thank you.